Hello everyone, my name is Zuyan Zhang. I'm from Information Engineering University. The topic I'm asked to speak on is Eiffel inferring importance of significant floating-point errors with polynomial extrapolation. I'd like to divide my presentation into four parts: background, difficulties, approach, and evaluation. Firstly, I would like to introduce the background of our research. So what is floating-point errors? For arithmetic expression, some inputs may trigger significant IP errors. For the following expression, the limit value when x tends to 0 is equal to 0.5. However, due to the existence of floating-point error, the calculation result double position floating-point numbers in computer has a large deviation from the real value. The fundamental reason is that computer final position floating-point numbers cannot represent the exact real numbers. So there is bound to be the rounding error, and the error will be magnified in the operation. When we use 120 bits to represent a floating-point number, we can see that the error is significantly reduced. As we all know, floating-point errors are a famous problem in software development, and a large rounding error may lead to catastrophic software failures, so error detection is crucial. Existing approaches include static and dynamic analysis. The goal of the static analysis to approximate error bounds, which is over-approximated. Dynamic analysis goal is to find the maximal error and corresponding input. It is a real error. We choose to research dynamic analysis. Second, I would like to introduce the difficulties about the guided searches. The percent of guided search is shown in the figure. The search space is D, and C1, C2, C3 are constraints of the two variables x and y. The points within R are input values that may trigger significant errors. P is the input that triggers the maximal error. The goal of the guided search is to find the P. Difficulties are D may be complex large, and R and P could both be many. Okay, now we move to the part of approach. The core idea of Eiffel is to infer error-inducing rings instead of searching them in D. First, the inputs are the arithmetic expression and the detection interval D. Next, perform the dataset construction across R. Then perform this clustering depending on the number of clusters to decide which method to perform. If number is less than or equal to 2, the maximal error is obtained by sampling directly on R. Otherwise, perform curve derivation, extrapolation, and simple in-range on D. For data set construction, there are two issues need to be resolved. First, we need to determine R. Because IP numbers are non-uniformly distributed, for example, a smaller range -1 to 1 covers 49.95% of all exactly represented IP numbers when using double precision representation. And the closer to 0, the denser the IP numbers. So we choose intervals as close to 0 as possible to cover more floating-point numbers. Second, we need to decide the number of the input values as to compute the URP errors. Considering the performance we set equal 500,000, it just costs 0.17 seconds. Considering real numbers are distributed uniformly and S is instantiated by a large value. We let S samples uniformly distribute across R. The goal of boundary extraction is reduce the number of data points to accelerate the clustering. Firstly, get the average equal 500 samples in one group. Secondly, preserve the one that has the largest URP error in every group. The fact is shown in the figure, and the goal of data clustering is obtaining the maximal error point for each cluster to fit the function. We use the depth scan clustering algorithm. Then perform curve derivation facing two challenges. First, each peak point is represented as a 2D coordinate. Deriving a mathematical function for the green curve is difficult. Eiffel may fail to find such a mathematical function or would require high execution overhead and introduce significant inconsistencies even if such a function can be found. Second, it is very likely to happen that the extrapolated points still follow the same distribution as that of the stars. which makes the error values of the extrapolated points equal to those of the stars. To resolve the first issue, we do not perform curve fitting on the peak points. Instead, we record their xi values, derive their distribution along R, and infer the x values of the extrapolated points. This simplifies curve fitting by converting the 2D coordinates into a 1D form, but extrapolation based on which may still be overfitting to address this. We assume the xi values of each peak points form a geometric sequence or geometric progression. Writing as below, where Q is a common ratio. The assumption is observed from extensive experiments. The figure on the right shows two happy benchmarks whose high error-inducing S values exhibit such a property. Most practical benchmarks also exhibit a similar property. Considering this assumption is made based on experimental observations, we compute a lower bound x minus r and an upper bound xi plus r, which form a range that covers each xi. Finally, we derive two curves that best fit the lower and upper bounds of each range. With two curves, we can derive the remaining intervals of induced high errors. As ranges are inferent, dynamically inspecting the largest error in each of such smaller ranges is possible. Among which the maximum error can be returned as the final result. We never require 1 or 2, we just return the dynamically detected maximum error across R. As the result, we never require 1, considering the figure on the left, due to its insignificant fluctuations, the depth algorithm assigns the large error points into one cluster. We can consider that such insignificant fluctuations also exist in D because this IP expression is numerically stable. The figure on the right is numerically unstable. If the significant errors are considered as nuances, Eiffel obtains only one cluster, otherwise they form two clusters. The maximum error of DR is very likely to be the result of an unduemess. When the number more than or equal to 3, we can combine with monotonicity. We can contact errors in a small range if an IP expression is monotonous. Next, Eiffel hand multivariate expression is similar to the single-variate case, but two adaptations should be introduced. First, project the multi-dimensional plot onto the variable space, which produce the variable continuous of the errors. For example, the figure is the 3D error distribution plot of the hyper benchmark from EpiBench. Eiffel obtains the projection results in the right figure. The depth algorithm is then applied to those points without changes, producing 3 clusters. Second, Eiffel performs curve fitting along 1 dimension at a time. It can produce hyper-rectangular rings, but is still more effective than existing approaches. Now we come to the last part, evaluation. A total 17 benchmarks were selected. 66 expressions are from EpiBench, and 4 expressions are from real-life numeric program. And there are 30 single-variate and 40 multivariate deciding using large but reasonable rings. For effectiveness, we compare with the state-of-the-art technical SRP and Tommy. Eiffel successfully detects the errors of all benchmarks. SRP returns empty results for 27 of them, while Tommy is unable to report errors for the 30 single-variate examples. For the quantity of inferred impurines, Regina fails to infer impurines at a large size of D. We also compared with PSAT. Eiffel can obtain more impurines than PSAT. For quality, we feed the inferred impurines to Herbie. In summary, the Herbie variant with our inferred impurines obtains an average accuracy improvement of 3.35 bits and up to 53.3 bits over the original Herbie version. Finally, Eiffel's time overhead is between Polynomial and I3FP. That's all for my presentation. If you have any question, please feel free to contact me. That's all. Thank you.